Hello students, I am Dr. Swadesh Gupta. I am assistant professor at Physics Department, DBS College. In this lecture, I am talking about the crystal structure, which is in the first unit. So, first thing is what is crystal? As we all know about the materials, that there are three phases: solid, liquid, and gas. So, of which solids can also be divided into two sections, which are crystalline and non-crystalline. So a crystal is a solid where the constituent atoms are arranged in a periodic ordered manner, and it is extended in the 3D space. While the atoms in a solid, if they are not arranged in any possible periodic manner, then they will be non-crystalline, and they are also termed as amorphous solids. So the crystalline materials or crystalline solid can be metal, other ceramics and polymers. While the non-crystalline materials are those materials which have complex structure and formed by the rapid cooling. Here you can see the crystalline SiO2 structure, silicon dioxide. So here it is arranged in some periodic manner, while in the non-crystalline silicon dioxide, you can see the structure is not uniform. So this is non-crystalline or amorphous. Now let's come to some important points. So as we already understood that atoms in a crystal are arranged in some regular manner, and if you see here, then there are different points, and the position of each atom in the crystal structure can be assumed as a point in space, which is called lattice point, and the group of this all lattice point is space lattice. If this space lattice has identical atoms everywhere on each lattice point, then this space lattice will called as Bravais lattice. The environment around each lattice point will be same everywhere. So if you choose any point in the space lattice, then the surrounding will be same. Now, when a crystal structure is formed, then there is a unit assembly of atoms, as you can see here. So this unit assembly of atoms have some special arrangement which is associated with each lattice point. So this unit assembly is called basis, and when the basis meets the lattice, then the crystal structure is formed. The basis of a crystal can have a single atom or more than single atom. Like for examples, aluminium and barium have single atom, while for NaCl and KCl the basis atom is 2, and for CaF2 it is 3, and so on. There can be more atoms. So what is lattice planes? A set of parallel equally spaced planes in a space lattice which include all lattice points are called as lattice plane. So in a single crystal there can be different lattice plane and which can have different orientation with each other. Now coming to the unit cell, so as from the name unit cell, you can understand that it is the most basic structure of a crystal. So that is why it is called the building block of a crystal structure. So a unit cell consists of a group of atoms which represents all kind of symmetry of a crystal. So make, if you need to generate a crystal structure from the unit cell, then you need to translate the unit cell along its edge in the 3D direction, and then you can create the crystal structure. Now, Lattice parameters. This is very important. So as you can see here, I have prepared a unit cell and there are three axes X, Y and Z. These axes are called crystallographic axes. These axes are along the edges of the unit cell. Now there are three intercepts A, B and C on these crystallographic axes which determines the dimension of the unit cell. There are another parameter alpha, beta and gamma. These are the three angles which are called interfacial angles. So the alpha is the angle between B and C, beta is the angle between A and C, and gamma is the angle between A and B. So the three intercepts A, B, C and three interfacial angles alpha, beta and gamma, these are called lattice parameters of a unit cell. So if we know these parameters, then we can actually know the size and shape of the unit cell. So if a unit cell has only one lattice point and it is provided that the lattice points are only in the corner of the cell, then such unit cell is called primitive cell. If the unit cell has more than one lattice point, let's say 2, 3, 4, then it will be called doubly primitive and so on. Now coming to the crystal system. As we already understood that there are two kinds of lattice parameter, intercepts and the interfacial angles. So according to these lattice parameters, there can be 7 basic crystal systems. So in the table you can see first is cubic crystal system. Here the three intercepts are equal to each other and also the interfacial angles are equal to each other, but the interfacial angles have one condition that all are 90 degree. The second crystal system is monoclinic where all the intercepts are different and the angle alpha and beta is equal to 90 degree while the gamma can have any value. Third is triclinic where again the intercepts have different values and interfacial angles also have different values and one condition is the angle should not be 90 degree. More are tetragonal, orthorhombic, rhomboedral, hexagonal depending on the different condition of these lattice parameters. So we have 7 different crystal structure, but as we have already discussed about the Bravais space lattice showed that there can be 14 ways of arranging the points in space so that the environment looks the same from each point. So for the cubic structure, it can be simple cubic, face-centered cubic, and body-centered cubic. Similarly, a tetragonal can be simple tetragonal or it can be body-centered tetragonal. Orthorhombic can be of 4 types: simple orthorhombic, body-centered, base-centered, and face-centered. The monoclinic can be of 2 types: simple and base-centered. So, in total, there can be only 14 ways by which we can have the Bravais space lattice. Now, few important terms regarding to the crystal structure. First is the number of atoms per unit cell. So in a unit cell, you can see there are number of atoms, but in actual calculation, there are not that much atoms belongs to single unit cell. So the effective number is called the number of atoms per unit cell. Second is the coordination number. Coordination number is the number of the nearest neighbor directly surrounding a given atom. Third is the atomic radius. Atomic radius is defined as the distance between the two nearest neighbors in a crystal of a pure element, and it is usually expressed in terms of cube HA, and the two nearest neighbor atoms touch each other. This is the condition. The next is atomic packing factor. So it actually defines that how much volume of a unit cell has been occupied by the atoms and is given by this formula. The voids are the space which is left in a unit cell, that is, which is unoccupied by the atoms. So in the next lecture, I will be teaching about the cubic crystal structure.